Okay, so today's lesson we're looking at a series of things called transducers, and transducers, all they do is they convert energy, and because we're looking about electricity here, it's electrical energy, so that we're looking at. So there's two types of transducers that we're talking about. Input. So input transducers would take some energy and convert it to electrical. Alright, so you know, a microphone would, for example, sound energy into electrical. So that would be input. So then that electrical energy then goes into something. So like in the case of a microphone, it might be an amplifier. Output, we take electrical and then into some other type of energy. And say if you were talking about a light globe, we'd be going electrical to sound, to light, I should say, not sound. Alright, so transducer, they convert energy. So first thing we want to look at in this topic is what we call voltage dividers. Alright, now voltage dividers are very common now in today's electronics. So essentially they look like this. Alright, so we might have some voltage coming in, V in, and that's more than what we need. So V out is over here, so we take it across. So V out, and remember V out here is in parallel with R2, so whatever the voltage here is on R2, it's the same as V out. So we want some lesser voltage. So we then choose those two resistors in a particular way so that we get the voltage that we want. Alright, so let's have a look at this circuit in a bit more detail. Alright, so the resistance of the circuit, forget about V out at the moment, so the resistance of that circuit on the left there, the total resistance, because they're in series, our total resistance is R1 plus R2. It's the total resistance of our circuit. So in that left hand side there, so forgetting about V out, but in that left hand side, we know that V in would be the current in the circuit times by the resistance of the circuit, which is R1 plus R2. Alright, so that's that. Now V out, I already marked there and I said it's the same as that there. So V out, in terms of Ohm's law, is that V out would be the current that's flowing through R2 times that resistance R2. Alright, so voltage divider, we'll have a look at that ratio. So V out over V in, let's have a look at them then. So V out, what we get out over what we put in, that ratio, would be I R2 over I R1 plus R2. Now you'll notice that current would cancel out, and so V out over V in is equal to R2 over R1 plus R2. Alright, so as I said before, by choosing our resistors, and I've just noticed my notes there when you look at them, there's a bit of an error there. So this is the correct one, not what my notes say. So we can, if we've got a certain voltage in and we want a certain voltage out, we can choose resistors in that way to figure it out. So there's an example that we're going to use to show you that. Okay, so here's the example. So we'll go back to the next page here. Now, I mentioned here that there's an error in my notes. My notes, I've got I on the top over R1 plus R2. That is incorrect. This one here is correct. Now, I'll endeavour to have that corrected by the time you guys see this, just in case I haven't. Keep that in mind. So this is what we're after. We're after that there. So V out over V in equals R2 over R1 plus R2. Alright, so what we've got here in this particular example, so something to point out, when you've got something like this is a typical electronic circuit where they have a positive rail in this case, so everything that's connected up here is 5 volts, and then down here we've got 0 volts. So across there, all the way across to there, is 5 volts. Alright, so that is our V in. Our V out, we've already been told that that's 4. And we've got a couple of resistors, this one R1, and that's what we want to try and find out, what that resistance is. And then R2, we've already been told. Alright, so let's put in some numbers. So V out, we want to be 4. V in is 5. R2, that resistor there is 22 kilo ohms, so kilo 2.2 by 10 to the 3. Kilo is 3, which is 2,200 ohms. So I'll write it as 2,200. And then on the bottom, R1, that's what we're trying to find out, plus 2,200. Alright, then do a bit of rearranging. So multiplying both sides by R1 plus 2,200 and both sides by 5. When we do that, we get this. You get 4R1 equals, oops, not equals, plus 8,800 equals 5 times 2,200 is 11,000. Take 8,800, then divide by 4, and you find that you need to set a R1 resistor at 550 ohms. Alright, so we've divided the voltage, and we now got what we want for 4 volts. Alright, so in this they called about this variable resistor, which is this one here, and what it needs to be. So variable resistors are quite common, and what they're called is they're called potentiometers. So here's in your notes, and I've got in your notes here, there's a diagram, so let's have a look at that. Alright, so here's our potentiometer. So on the left there, there's all different shapes and sizes of these things. Then on the right, there's kind of a bit of a schematic about what they are. So A and W are our key things. So the red bit there, as it says, is a resistive element, and this W one in the middle is connected to the rotating dial. So, you know, like that bit there. And so what happens is this part of it can move. If you twist it, you can move it left or right, and moving it left or right changes the position it is on that that red resistor. So if it's up here, there's less resistance. If it's up here, there's more resistance. So that variable varies the resistance. Well, that's better. So variable resistance, and so therefore we can change that resistance easily. So potentiometer, you might think it's not really an input, transducer, but in fact it is, because we can change a signal, so we can change that resistance and change that voltage. So it's a processing element. All right. Okay. So if we have a look at a diagram which shows a schematic diagram, circuit diagram. All right. So here's circuit diagram, what they'd be. So you see that they look very similar to what your voltage dividers were. This top one here is a little bit confusing. This one here is a little bit more. So you can see here, and here as well, there your potentiometer, and that arrow's that middle bit, and so we can move that, and by moving that we can change the resistance. Alright, so that's what they look like. Now, right up the top of that web page, there's a document there that shows you all the different symbols. So potentiometer, it's like a resistance with an arrow on it. So as I said back here, moving this part changes the resistance. So that's the part that's got the arrow on it. Now these are very, very common. Things like volume controls. Okay, potentiometers are used in things like volume controls on audio equipment, although there are some these days that don't have that, but any that's got a dial, it's quite likely to have that particular thing in volume control. Alright, so let's have a look at some other input transducers, and the next one is a thing called a thermistor, and it's an input transistor. And the thing with a thermistor, and the therm part, it has to do with temperature. And what happens with the temperature is that the resistance changes with temp. And the resistance changes with temperature in particular ways. Now, they take temperature, thermal energy, and they convert it into electricity. So they're thermistors, input transducers. And let's have a look. Right, so here's a diagram, and so here, this is the symbol of a thermistor. So it's like a resistor with a little line through it, so it changes. Now, when you get thermistors, you will always have a data sheet with them, and the data sheet will give you their characteristics. So I'll just look at option B there at the moment. So option B, for example, so if you have a temperature of 60 degrees down here, then what it has a resistance of that, whatever it is, about 0.4 kilo ohms. However, if the temperature's 10 degrees, then it has a resistance of 2 kilo ohms. So that changes. So things like temperature sensors in fridges, ovens, that sort of stuff, thermistors would be used for. Now the one on the right there, option C, so you'll notice there's 3 lines. So what that is, data for 3 different thermistors. You'd have to be able to told which it is. You'll notice that the graph paper there is a bit different as well, and this is because it's log graph paper. So on the vertical axis up here, all right, we're going up by a factor of 10, so 10, 100, 1,000, and so on. All right, so you would need to know which of the thermistors the line, and again, you'd same, you would just read them off. All right, so let's have a look at an example of the thermistor. All right, so here's our diagram. Here's our thermistor is here, so our resistance of that is going to change depending on the temperature. Now we're told figure 4.8c above the bottom curve, alright, so the bottom curve. So remember, when flick back there, so there was 3 curves, so we're interested in the bottom curve. Alright, so we use that to find resistance of the thermistor, and then we would use whatever it is we need to use. In terms of, you know, Ohm's law or power equations or anything like that. So part A simply asks, what is the resistance of the thermistor when the temperature is 150 degrees Celsius? Alright, so what we need to do is we need to go here, here's 150, and so we go up there, and that's the second one above the 10. So the second one above the 10, the way the log thing works, so if that's 10, then the next one above it is 20, the one above that's 30, and so on. So the resistance of that particular thing is 20 ohms. Alright, part B. Part B says, what is the value of the variable resistor? There's that one there. If the value, if the temperature is 200, I should say, and V out is 6 volts. Alright, so we've got some information. So we know V in is 9, V out we're told is 6. We know the temperature, so let's go back here, and from the temperature of 200 we go up to here and then go across, and so that's 10 ohms. Alright, so let's have a look. This is the information we've got. We've got V out equals 6, V in equals 9, R2 was 10 ohms. So that's the resistance of that thing at. Alright, so we then go V out over V in is R2 over R1 plus R2. Put in the information that we've got. We want 6 out, we've got 9 in, R2 is 10, R1's what we're after, R2 is 10. Alright, multiply both sides by R1 plus 10 and both sides by 9, and then you would get 6 lots of R1 plus 60 equals 90. Take 60, divide by 6, and you find that your variable resistor has to be set at 5 ohms for you to get what you want. Alright, the next part of input transducer, I should say, is a thing called a diode. And in modern electronics, diodes are extremely common, and they have very interesting characteristic. And that their interesting characteristic is that current can flow in one way. And so the symbol for the diode looks like this. And what that indicates is that your current can flow this way, but not the other way. So if we wanted to have current this way, it doesn't work. So they're very interesting in that when the current flows the right way, in the direction that the arrow is pointing, it's low resistance, but the other way is high resistance. Here's a bit of a diagram. Alright, so the couple up the top there, we've just got a couple of resistance. So this one here is what we would call forward bias. Alright, so conventional current, positive to negative, so it's in the forward bias, it's the right direction, it's the way the arrow points, so this acts as very low resistance, effective, very close to zero. In the second one, this one here, that one is what we call reverse bias. Because we're trying to get the current to flow the direction it's not, and so you've got the line there, it's like the wall, you can't get through the wall. Alright, and so when we have reverse bias, it's a very high resistance, so close to infinity. Alright, so again with diodes you would have a data sheet and so a characteristic and show the voltage current characteristic, and here's one there below. So you see that when we're trying to get the current flow in the reverse direction, you see we really don't get anything much at all, so very high resistance. But in the forward direction, and then it takes a little bit, but in the forward direction, it's a little bit of resistance, but then eventually takes off. And so we would then have very low resistance, and that one here is kind of at about 0.7 volts. So after 0.7 volts, boom, very low resistance. So in the notes there, it just talks about the curve, the top part low resistance. In the forward bias, very low resistance, so forward bias is that part here, and the reverse bias is this part down here. Alright, so let's have a look at an example. So here's our example. The EMF of supply circuit is 10 volts, so that's here. And the value of the resistor is 100. Estimate the current flowing through the diode. Now you would need to be given some information, and the diode, now I've given you a bit of information here, the diode can be assumed to have a voltage drop of 0.7. So we've got 0.7 across the diode, we've got to have a total of 10. So 10 has got to equal the 0.7 of the diode plus the voltage over the resistor, I'll call it. And so the voltage across the resistor, therefore, it's got to be 10 minus 0.7, which is 9.3 volts, which it says there. Alright, So if there's 9.3 volts across the resistor, and oops, I wanted to change that colour, and then Ohm's law says V equals IR, and so we're now talking about resistor, remember, so the voltage across the resistor is 9.3. The current is what we are after. Whoops, not equals, times by the resistance, which is 100, and so divide by 100, I equals 0.093, which you would probably more likely see written as 93 milliamps. Okay, so milli, power of 3, 1, 2, 3. Alright, now there's a little note there that's in there, in your, so that was forward bias, so that's alright, conventional current flowing around this way, and that's all good. But just remember, you need to check, because if it's reverse bias, such as is the case here, so in this case here, we're trying to send the current around that away, and when we look at the diode, we'll notice that it's in the reverse bias, it's got its wall up, won't let it get through. So what actually happens now is what it says is that the whole 6 volts at the battery all gets used up here, so there's nothing left for the resistor, and our current is effectively, it's equal to 0 amps. Now, of course, in reality, that's not quite. So for low voltages that this component works in, like 6 volts, it works alright, that's good, but you can bust these things if you put 1000 volts across it, then it's going to get broken and you can force current through. But for our purposes, we're talking about in the normal operational zone of these things. Alright, so that's one. Here's another one. Another one, light dependent resistors. Alright, and light dependent resistors, their resistance varies with the light. And generally it gets less when the light, the brighter the light, the less the resistance generally. Now, you can see these called as LDR, just the first letters of each. Now, of course, with these light dependent resistors, same as the last two, we would get some sort of data sheet that tells us about the characteristics. And so here's an example of one. Alright, so there we go. So here's our light dependent resistor. So depending on what the illumination is, and then we can find out the resistance of it, depending on what the illumination. Now you'll notice this graph paper is a bit different again. It's log this one, so you got log on both axes. Alright, and so it all goes up by powers of 10 as we've mentioned. There's a little bit more of an explanation on there. So if this line here is 10, then this next one is 20, that one there is 30, 40 and so on until you get to 100, and then this one's 200, 300 and so on. Alright, let's get rid of those lines there. Symbol for light dependent resistor. So, you know, just this boxy thing here is the resistor. Arrows light coming in. Alright, example. Let's have a look at an example. Alright, Righto, here's our example shock minder. So, you know, when you work through the shocks and it goes ding ding, shock minders are you have a light shining across there, you walk through, cuts the light going to the light dependent resistor, and then it goes off. Alright, so there we go. Again, you notice another voltage divider. Voltage dividers, as I said earlier, we looked at them earlier, very common. Alright, so we've got 12 volts that acts on. We've got a resistance here, variable one. We've got our light dependent resistance, V out and V in, of course. So for question first up says, well, what is the resistance of the light dependent resistor when the light intensity is 1 lux? Alright, and it says up here to use the characteristic above. So here's the characteristic above. 1 lux, so 1 lux is here, we go up to there, and then we come across and it looks like it's 1,000. So here we go, so for A, it's 1,000 ohms, which of course is 1 kilo ohm. Alright. The next one, part B. Part B says, if the variable resistor is set at 500, calculate the value of V out when the light intensity is 1 lux. Right, I'm not going to have enough, so I'm going to have to flick backwards and forwards here. So, information that we have is, we know that, wrong way. Alright, so, V in is 12, V out is what we're after, so V in is 12. We need to know R1 and R2, so having a look at that. Variable resistor set at 500, so that's R1. And R2 at 1 lux was 1,000. So we want to know what the voltage out is, so V out over V in equals R2 over R1 plus R2. So V out over 12 equals 1,000 over 500 plus 1,000. And then times both sides by 12, so V out equals 12 times 1,000 is 12,000. Over 1,500, and then when you get your calculator out, you find that that is 8 volts. Alright, part C, let's go back, see what part C's got to say. Part C says, what is the value of the variable resistor? Light intensity of 0.1 lux and V out is 6. So for part C, we've got V in is 12 still, V out is 6, not V, but R1 is what we're after, and R2, that's our light dependent resistor. So let's go back, 0.1 lux, 0.1 lux, 0.1 lux is 0.1 lux right here down the bottom, 0.1 lux, 10,000 ohms by the looks of it. Right, so here we go, 10,000, squeeze it in, 1, 2, 3. Beautiful. Alright, so when we just use the same as we did before, V out over V in, so 6 over 12 equals R2, 10,000 over R1 plus 10,000. A bit messy here. Then rearrange times both sides by R1 plus 1,000. You get that 6 R1 plus 6,000 equals 120,000 times in both sides by 12. Take 6,000, divide by 6, and you find that R1 needs to be set at 10,000 for us to have 6-volt output at R1. Alright, so that's a bunch of input transducers. Now I'll look at some output transducers. So light emitting diode, or as we commonly know them as LEDs. They're told them a lot, about them a lot, and so they emit light. So they're just diodes, kind of diode that emits light, and so if it emits light, it's got these arrows, so it's and they're very, very, very common these days in everything, just very lots and lots of stuff. Alright, so why? Well, we're more durable. Right, not like normal ones. So the other one, low voltage. Alright, so, you know, typically between 1.6 and 2.8 volts, so low voltage. So long life, you know, they don't have that tungsten wire that's heated up and cooled down and heated up and cooled down. So fast response is another one. And less power to run them. So that's why LEDs are seen to be very handy, very useful. Are used in heaps and heaps of stuff. Automotive, traffic lights have them now, you know, lights in houses, everything has light emitting diodes these days. And the technology's been improved and improved and improved all the time. Big market these days. Alright, so let's have a look at an example. Alright, so same kind of stuff as before. Let's have a look here. The LED is shown as a voltage drop of 1.8 volt across it. The current flowing is 20 milliamps. What is the voltage drop across the limiting resistor? Well, there's 6 volts altogether in this series circuit, and remember, around series circuits, voltages add up. So the 6 volts that we've got, there's got to be the voltage at the resistor plus the diode, which is 1.8. So the voltage across the resistor then is 6 minus 1.8, which is 4.2 volts. Alright, so then we're asked in part B, what is the value of that resistor? So what we know then, that we've got a voltage across there of 4.2. We know the current going through it because the series is current is the same. So just using Ohm's law, so B right, V equals IR. And the voltage, let's go back to line 4.2, current 20 milliamps. So 4.2 equals 20 milliamps, so that's 20 milli 10 to the minus 3 times the resistance, divide both sides by 20 by 10 to the minus 3, and you find that the resistance of that resistor is 210 ohms. Alright, a long one today, a fair bit of stuff in that, so a bit to digest. So just a bit of a summary. So transducers convert energy, and we're looking at converting either into or out of electrical energy, and there's a whole bunch of examples of things that you were given, and you would in questions need characteristic diagrams, graphs, so that you can get information from that. Alright, questions in your textbook, and of course make sure you ask if you need help with any of this stuff.